Welcome back. Today I'm going to tell you about lipid and sugar. So what do you know about the lipid and sugar? Today I have a friend of mine from Singapore, Professor Shin from Singapore. Welcome.
Hey,
Welcome. Hey.
Sensei. Okay.
Good to see you.
Yeah.
So he's from Singapore. What do you know about Singapore?
What
do you know?
about Singapore?
Malaya. Okay, that's
Malaya,
famous.
yeah.
Right. So he's going to be able to tell us about carbohydrate basics.
Yes.
Okay, go ahead.
What is carbohydrate in your mind? Very important molecule that is glucose. We take glucose every day. And I can tell you glucose is the typical structures among these 8 structures. Which one is glucose? Can you tell me?
This one.
Ah, perfect. This is the typical chemical structures of glucose. This is a linear form and a lot of OH groups located in these structures. That is a typical chemical structures for glucose. And in nature, there are many very similar structures as glucose, which are listed here. At the very beginning, the first impression very similar. But I can tell you clearly, they are very different molecules.
Here is galactose. What
Yeah.
is the difference between glucose and galactose?
That is a very good question. For these 2 structures, you can see both of them, they have a 6 carbon. They have the same numbers of OH group with one aldehyde group on the top. If you look at the structures very carefully, only one location you can see is different. What location is different? You can see this OH group. For glucose, OH group point to the right hand side. But you look at carefully for this one, change. This is point to the opposite direction. I can tell you, glucose you can take can produce energy, but the galactose may not give you enough energy. Why? Because they are different molecules.
Okay.
This is 2 typical reactions for carbohydrate. And you know that carbohydrate structures contain a lot of OH groups. They have an aldehyde group, or we call them carbonyl groups. But I can tell you, if carbonyl group mix with OH groups, some potential reactions may happen, as I show you here. If your functional groups contain aldehyde, if you have OH groups, they can have a condensation to form these tetrahedral structures with one OH group free. For these structures come from aldehyde, we call them hemiacetyl. If you have the other OH group around, these 2 have condensation reactions to form this acetyl. Very important reactions. If your carbohydrate contain the carbonyl, which is the ketone group, they have a similar reactions. You have an OH group around, they can form tetrahedral structures. We call them hemiketo. Keto means from ketone. Here is one free OH group. If you have the other OH group around molecule, they have a condensation reactions to form these keto structures. Very important reactions. Why? I can explain later. You understand what this slide is talking about?
Of course.
You okay?
Right. Yeah, I'm a good student. So what about this one?
Okay. At the very beginning, I already introduced. Glucose is a linear form. And we use a typical Fischer projection to visualize this linear form structures. But I can tell you very interesting thing for glucose. In our life, in our body, glucose exists in kind of aqueous solution. And in the aqueous solutions, very hard to find the linear form glucose anymore. Most of the glucose in our body, in the aqueous solutions, form as ring structures. And the previous slides I introduced the reaction. That is the reaction help this linear form glucose folded each other to form these ring structures. You know the basic chemistry? sp2, hypertidation. You know where's the hypertidation for these structures?
Here.
I'm sure you're a very good student. Huh? Okay, carbonyl in chemistry is planar structures. So that is sp2 hypertidation. So when the OH group folded each other close enough each other, they may have reactions as I mentioned before. So your linear form structures OH group may have reactions. You have two possibilities. One from bottom, one from up. This is why you have two ring products after the reactions.
Why do you have P-line structure here?
Oh, that is also very good point. Okay, this is a typical the ring structures, a six-member ring. Long time ago, when scientists they try to study the chemical structures of glucose, they want to use something to mimic. So let's see, 100 years ago, not much understanding of chemical structures, and they only have a few examples. This is the typical example, purine. Everybody knows purine is kind of a six-member ring structures. And the glucose is very similar. This is what people use the purine to mimic the glucose structures. Because this structure from glucose, so we call them glucopyranos. As I just mentioned, the reaction can be two possibilities. This is why we always have two ring form structures for glucose. One is alpha form, one is the beta form. And also to simplify the structures, people link in this way. This is all the real structures in nature.
Okay.
Okay. Carbohydrate structures not so simple. You can see six-member ring. And in the real case, the carbohydrate, the ring form structures exist as a chair form. Because the chair form in nature is kind of a stable structures. I can also tell you the different OH group, they can locate it at the six-member ring structures chair form at a different direction. If the OH group, for example, this one point in the straight way, like this, so we call this glucose structure as kind of axial chair form structures. And if the OH group located as kind of link structures, all of them link structures, so we call them equatorial structures, which is quite complicated. You understand what this? Okay.
Go ahead.
In the chemistry, all we know, or in nature, any molecule, if they have six membrane structures, which is a stable structures, can exist for a long time. And I also can tell you, for some of the ring structures, if they have a five-member ring, is also kind of the stable structures. And in nature, sometimes we can find, besides the six-member ring of glucose, you can also find carbohydrate glucose can exist as five-member ring. Since it's already
DNA is like that.
Oh, that is,
Right.
you are the expert in DNA, huh? I know. So if that is a five-member ring, you cannot call them purine anymore. You have to call them furanols. This is different carbohydrate structures. You know something about the different carbohydrate apart from the glucose?
Different carbohydrate apart from glucose.
Yep.
Mannose.
Ah, good. I just introduced.
Yeah.
Carbohydrate structures in nature not only exist at the one single 5 membrane or one single 6 membrane. And the carbohydrate molecule, they really can form covalent bond. They can link up each other to form oligomer or polymer structures. Some of the structures link up as a, linear form. Linear form. And some of the structures can form as a
Circular.
Yes, circular structures.
There are many examples. For example, what is this? It's circular.
It is a typical
oligosaccharide.
the molecules actually every day we can experience. Every day we take rice. The major component of rice actually is the starch. That is kind of a polymer structures of glucose. For that, the polymer structures, if we have some or partial hydrolysis, we can get these small reform structures.
Oligosaccharides are usually sweet. I mean,
Yes.
when they are digested.
Correct.
But what about this? This is from apricot. Is this sweet too?
Oh, that is a very good question. In nature, in general life, everybody talk about the sugar. Wow, it's very sweet. But in nature may not be always the case. Some of the carbohydrate, we call them sugar, but the taste is very bitter. This is a very good example. Sometimes some friends, they enjoy to take the nuts. Okay, many of nuts, let's say from apricots, tastes very sweet, a lot of nutrients inside, but this is exceptional. This is the sugar you take very bitter.
Okay, I think that's it. Thank you very
Okay.
much for coming.
Oh, thank you.
Yeah. So do you remember what is famous about Singapore?
Singapore.